Tonight, we're going to explore a measurement that sounds simple but changes everything once you truly understand it. A light year. You've heard this term before. Scientists use it constantly. Astronomers throw it around casually. That galaxy is 2 million light years away. The nearest star is 4.2 light years distant. But here's what most people miss. A light year isn't about time at all. It's about distance. And when you really grasp what that distance means, when you actually feel it, it changes how you see the universe, how you see Earth, how you see yourself standing here, right now, under all those distant stars. This journey we're about to take together, it's not rushed. We're going to move slowly, deliberately, because understanding light years isn't about memorizing numbers. It's about letting the scale of the universe settle into you, about feeling the distances in a way that numbers alone can never convey. Before we begin, if you enjoy these kinds of explorations, a like or subscribe helps tremendously. It's a small gesture, but it allows me to keep making these journeys into the cosmos, these slow, contemplative dives into the questions that matter. Now, let's start somewhere familiar. Think about walking to your local coffee shop. Maybe it's half a mile away, about 800 meters. You know that distance. You've felt it in your legs, seen the landmarks along the way, experienced how long it takes. That's a human distance. We evolved to understand these scales. The distance to water, to shelter, to the next valley over. Our brains are built for this. Close your eyes for a moment and picture that walk. You know exactly how it feels. The first block where you pass the red brick building. The intersection where you always wait for the light. The stretch where the sidewalk is uneven and you have to watch your step. The final turn where you can smell the coffee even before you see the shop. That distance isn't just a number to you. It's textured with experience, with memory, with the accumulated weight of dozens or hundreds of times you've made that journey. A kilometer, that's about 0.6 of a mile, is roughly a 12-minute walk at a comfortable pace. You can picture it. You know what 12 minutes feels like. The grocery store might be 5 kilometers away, about 3 miles. That's maybe a 10-minute drive. You pass familiar streets. You stop at traffic lights. The distance has shape, context, meaning. Think about the route you take most often. Maybe it's to work. Maybe it's to a friend's house. Maybe it's the path you walk when you need to think, to clear your head, to process something difficult. You know every turn, every landmark, the tree that marks the halfway point, the building where you always glance up, though you're not sure why anymore. It's just become habit. The intersection where the light always seems to catch you, where you stand and wait and watch people cross in the direction. These distances are woven into your life. They're part of your daily experience. Your brain doesn't just understand them intellectually, you feel them in your muscles, in your sense of time, in the rhythm of your routine. When you walk that familiar route, you're not thinking about the distance. You're thinking about what you'll do when you arrive, what you'll order at the coffee shop, what you'll say to your friend, what you need to buy at the store. The distance itself has become automatic, absorbed into your body's memory. Your legs know how long it takes. Your lungs know how much breath you'll need. Your mind can wander while your body handles the navigation. Your great-great-great-grandparents understood distances like this. They walked to the well, to the market, to the next farm over. The scale was the same. A mile was still all a mile. 20 minutes of walking on a good road. An hour if the road was bad or you were carrying something heavy or the weather turned against you. For thousands of years, human beings moved through the world at walking speed, 3 or 4 miles per hour at a steady pace, sometimes on horseback, faster but not dramatically so. Maybe 3 times walking speed, still measured in hours and days. The world was measured in how many days it took to walk somewhere, how many weeks of travel, how many months of journey. London to Edinburgh, about 10 days on foot. That's how you measured it. Not in miles, though miles existed as a unit. In days, in the experience of the journey, in how many times you'd sleep on the road, how many towns you'd pass through, how many times you'd need to stop and rest. And this is important to understand before we go further. Distance, for most of human existence, was inseparable from time and effort. You couldn't separate them. They were one thing. The distance to somewhere was the time it took to get there, was the effort required to cross it. A place that was far away meant days of walking, weeks of travel, preparation, planning, saying goodbye to people you might not see for months. Even the concept of far was different. What we'd consider a short drive today, 50 miles, was a significant journey, a day and a half of walking, an overnight stay somewhere, a commitment. Now, let's scale up. New York to Los Angeles, about 2,800 miles. That's 4,500 kilometers. It's a 5-hour flight. You cross the continent. You watch the landscape transform beneath you, cities to farmland, to mountains, to desert. It's far, yes, but it's achievable. People make this journey every day, thousands of people. It's routine, mundane even. I want you to really picture this for a moment. Not just the numbers, the experience. Imagine you're on that flight. You take off from JFK or Newark in the morning. The plane climbs through grey Atlantic weather, through clouds, breaking into brilliant sunshine above. Below you, the dense urban sprawl of the Northeast, New York City's impossible density of buildings, then Philadelphia, Baltimore, the corridor of cities stretching down the coast like beads on a string. Then the landscape opens up. Pennsylvania's rolling hills, green in summer, covered in snow in winter. The Appalachian Mountains, older than bones, worn down by time into soft curves. Ohio's flat farmland stretching to the horizon, perfectly flat, the curvature of Earth visible at the edges. The Great Plains of Kansas and Oklahoma, where you can see for what feels like forever, where the sky becomes the dominant feature, huge and overwhelming. The land looks quilted from above, divided into perfect squares of different crops. Wheat fields gold in summer, cornfields green, fallow fields brown. Section lines cutting exact grids across the landscape. You see rivers winding through the landscape like silver threads, catching the sunlight. Roads cutting straight lines across the plains, following section lines. Towns appear as small clusters of buildings, swimming pools like bright blue dots in suburban backyards. Irrigation circles making green circles in otherwise brown land. Then the Rockies rise up, dramatic, snow-capped even in summer, sharp and young compared to the Appalachians. The plane might bounce a bit in the mountain turbulence, the air unstable where it flows over peaks. You see tiny towns nestled in valleys, ski resorts clinging to slopes. The peaks look razor-sharp from above, casting long shadows across valleys. You can see where avalanches have carved paths through forests. And then the Southwest, Utah's red rock country, striations in the stone visible from 35,000 feet. Millions of years of geological history written in colored bands. Nevada's stark desert, where you can see dry lake beds, perfectly flat and white, and the occasional mining operation carving terraces into mountainsides. The land looks almost Mars-like, rusty and alien, hostile to life. Finally, California, the Sierra Nevada, still snow-covered on the highest peaks even in July. The Central Valley, agricultural and green, an engineered landscape of crops and canals. And then the Pacific coast, where the continent ends, where the water stretches away to the western horizon. You can see the curve of Earth at the edges of your vision, the way the ocean bends away from you. So here we are, at the end of our journey through light years and cosmic distances. We've traveled from the familiar to the incomprehensible, from the distances you walk every day to distances that light itself takes billions of years to cross. We've learned what a light year is: 9.46 trillion kilometers, 5.88 trillion miles. The distance light travels in 1 year, moving at 300,000 kilometers per second, the fastest possible speed in the universe. We've used this measurement to understand our place in the cosmos, to measure the distances between stars, between galaxies, across the observable universe itself. And in doing so, we've confronted something profound. Earth is tiny, almost incomprehensibly tiny, a speck of dust in a vast cosmic ocean. If you scaled the observable universe down to the size of Earth, our actual planet would be smaller than an atom, smaller than a proton. It would effectively not exist at any scale we could detect or measure. But here's the paradox at the heart of existence. Earth's smallness doesn't make it meaningless. In fact, it might make it more precious. Because as far as we know, and we've looked, we've searched, we've listened, Earth is the only place in the universe where life exists. The only place. In all those 2 trillion galaxies, in all those hundreds of billions of trillions of stars, in all those quintillions of planets, we know of exactly one that has life. One where water flows, one where forests grow, one where animals move and breathe and reproduce, one where consciousness has emerged, Earth. This might not remain true. We might discover microbial life on Mars or in the oceans beneath Europa's ice. We might detect signs of life in the atmospheres of distant exoplanets. We might receive a radio signal from another civilization, proof that we're not alone. Or we might search for centuries and find nothing. The universe might be full of dead worlds, rocks and ice and gas, following the laws of physics, but empty, lifeless, silent. We don't know yet, can't know yet. Our search has barely begun, but right now, in this moment, Earth is the only confirmed example of life in the entire universe. The only world we know where consciousness exists, where beings can look up at the stars and understand what they're seeing. And you're part of that consciousness. You're part of what makes Earth special. Think about what that means. You're made of atoms forged in the hearts of stars that died billions of years ago. Stars that fused hydrogen into helium, helium into carbon and oxygen, building up the elements through nuclear fusion. Stars that ended their lives in supernova explosions, scattering their atoms across space. Those atoms, your atoms, drifted through the galaxy for eons. They were part of vast clouds of gas and dust. They witnessed the births of new stars. They orbited the galactic center dozens of times over billions of years. Eventually, about 4.6 billion years ago, they became part of the cloud that collapsed to form our solar system. They were there when the sun ignited. They were there when planets coalesced from the disk of material around the young star. They became part of Earth. Over billions of years, those atoms have been recycled countless times. They've been part of the ocean, part of rocks, part of the atmosphere, part of countless organisms: bacteria, algae, ferns, insects, fish, dinosaurs, mammals. Each time an organism died, its atoms returned to the environment, ready to become part of something new. And now, right now, some of those ancient stellar atoms are part of you. The iron in your blood was created in a dying star. The calcium in your bones, the oxygen you're breathing right now. All of it came from stars. You are literally made of stardust. This isn't poetry, this isn't metaphor, this is literal truth. You're made of the cosmos. You're the universe in human form. And more than that, you're a way for the universe to know itself, to look at itself, to understand itself. For most of cosmic history, the universe was unconscious. Matter followed the laws of physics. Stars formed and died, galaxies spun, planets orbited, but none of it was aware. None of it knew it existed. None of it appreciated its own existence. Then somehow, somewhere, here on Earth at least, and possibly elsewhere, matter organized itself into patterns complex enough to achieve consciousness, to become aware, to look out at the cosmos and understand what it was seeing. That's you, your consciousness, your awareness. You're the universe looking at itself with comprehension. And that's extraordinary. That's precious. That's worth celebrating, especially if you're ultimately insignificant on a cosmic scale. Because significance isn't about size. It's not about how much space you occupy or how long you last. A galaxy is billions of times larger than Earth, but as far as we know, a galaxy isn't aware of itself. It doesn't know it exists. It doesn't appreciate its own spiral arms or its star-forming regions. It's just matter following physics. You, on the other hand, tiny as you are, brief as your life is, you're aware. You know you exist. You can look up at the night sky and feel wonder. You can understand, at least intellectually, what you're seeing when you look at the stars. You can appreciate the beauty and vastness of the cosmos. That awareness, that consciousness, that ability to understand and appreciate, that might be rarer than all the stars combined. So when you feel small, when life feels overwhelming, when you're stressed or anxious or worried, remember this journey we've taken tonight. Remember the light years. Remember the vast distances. Remember that you're experiencing all of this on a planet 7,926 miles across, orbiting a star 93 million miles away, in a galaxy 100,000 light years across, in a universe 93 billion light years across. Your problems are real, your pain is genuine. I'm not dismissing them. They matter to you, and therefore they matter. But they're also temporary, local, contained to this tiny world for this brief moment. From a cosmic perspective, they're small. They'll pass. You'll get through them. Earth will keep orbiting the sun. The stars will keep shining. The universe will continue its slow evolution, completely indifferent to human concerns. That doesn't make your problems less real to you, but it might make them more bearable. It might give you space to breathe, to step back, to gain perspective, to see them as part of a larger context. And when you feel joy, when you experience beauty, when you connect with another person, when you witness something that fills you with awe, remember that too is happening here on this small world and is precious precisely because of its smallness and brevity. The sunset is beautiful not despite being temporary, but because it's temporary. It only lasts a few minutes, and then it's gone. That makes it precious, worth paying attention to, worth savoring. The connection with another person is meaningful not despite being confined to this tiny planet, but because of it. Out of all the vastness of space, out of all the possible times and places, you and that other person exist here, now, together. You share this small world. That's remarkable. That's special. The moment of understanding, when something clicks, when you grasp a concept, when you see how things fit together, that's happening in your brain, in this moment, on this planet. It's a brief spark of comprehension in an often incomprehensible universe. Treasure it. Tonight, when you go outside, I want you to look up. Really look. Don't just glance at the sky. Actually, look at the stars. Find a dark place if you can, away from city lights. Let your eyes adjust. And look. Those points of light you see, each one is a sun. A massive ball of fusing hydrogen, converting matter into energy, pouring light out into space. Some are larger than our sun. Some are smaller. Some are young, hot, and blue. Some are old, cool, and red. Some are dying, approaching the end of their stellar lifetimes. And the light you're seeing has been traveling for years, decades, centuries, millennia. It left those distant suns in the past, sometimes the distant past, and has been crossing empty space ever since, traveling at the speed of light, the fastest possible speed in the universe. That light has traversed light years of emptiness. It's crossed distances so vast that our minds can't truly comprehend them. It's journeyed through the void between stars, through regions of space where there's almost nothing. A few stray atoms of hydrogen, some cosmic rays, some dust, but mostly just emptiness. And it arrives tonight at your eye. It crosses your cornea, focuses through your lens, strikes your retina, triggers a cascade of chemical reactions in your photoreceptor cells, sends electrical signals through your optic nerve to your visual cortex, and creates the experience of seeing a star. You're connected to that distant sun across both space and time. Connected by photons that have crossed the cosmic void, connected by the light itself. And you understand what you're seeing. You know those aren't just pretty lights in the sky. You know they're suns. You know they're light years away. You know the light has been traveling for years or centuries to reach you. You know you're looking back in time, seeing those stars as they were when the light left them, not as they are right now. That knowledge, that understanding, that's the gift. For most of human history, our ancestors looked up at the same sky. They saw the same stars, but they didn't know what they were seeing. They created beautiful myths and stories to explain the lights in the sky. They imagined gods and heroes and creatures painted across the heavens. Those stories gave meaning and structure to the night sky, but they didn't know the truth. Didn't know the stars were other suns. Didn't know the vast distances involved. Didn't know they were looking back in time. Didn't know they were seeing light that had traveled for years or centuries or millennia. We know now. We've figured it out. Through careful observation, through mathematics, through the patient accumulation of knowledge over thousands of years, we've learned the basic structure of the cosmos. We know Earth orbits the Sun. We know the Sun is a star, one of hundreds of billions in our galaxy. We know our galaxy is one of trillions in the observable universe. We know the universe is expanding, that it had a beginning, that it's 93 billion light years across. We know all this. You know all this. That's extraordinary. You live in a time when humanity understands its place in the cosmos, when we've measured the distances to the stars, when we've discovered that space is measured in light years, units so vast they defy human comprehension, yet we can calculate with them, use them, understand them. That's a privilege, a gift. You get to know things that our ancestors could only wonder about. You get to understand the universe in ways that were impossible for most of human history. And that knowledge doesn't diminish the wonder. If anything, it deepens it. Because now, when you look up, you're not just seeing pretty lights arranged in patterns. You're seeing across light years. You're seeing the universe in all its true scale and grandeur. You're witnessing the cosmos as it actually is, vast beyond comprehension, filled with wonders, governed by laws we can understand. You're part of it. Small, yes. Brief, yes. But part of it nonetheless. You're made of stardust. You're the universe experiencing itself. And for this moment, right now, tonight, as you read these words or look up at the stars, you're alive, conscious, aware, understanding. That's enough. That's everything. The universe is vast. You are small. Your life is brief. The distances are measured in light years, and those light years stretch far beyond anything you could ever hope to cross. But you're here, now, in this moment. You get to see this. You get to understand this. You get to be part of the cosmic story. Thank you for taking this journey with me, for traveling from the familiar to the incomprehensible, for imagining distances measured in light years, for confronting the vastness of space and your own smallness within it. I hope when you look up at the stars tonight, you see them differently. I hope you see them as distant suns, separated from us by light years of empty space. I hope you feel connected to them, connected by the light that crosses those vast distances, connected by the atoms you share, connected by your ability to look up and understand what you're seeing. The stars are waiting. The light has traveled light years to reach you. The universe is revealing itself to you, showing you its vastness and beauty and mystery. Look up, see, understand. Feel the weight and wonder of it all. You're standing on a small world, looking out at infinity, understanding your place in the cosmos. You're tiny, but you're conscious. You're brief, but you're aware. You're insignificant by cosmic measures, but you're the universe's way of knowing itself. And that's remarkable. That's precious. That's worth celebrating. The universe is vast. You are here. You are aware. And you understand. That's the gift. That's the meaning. That's what light years teach us. Not just about the scale of space, but about the preciousness of consciousness in a vast, mostly unconscious universe. Good night. Sleep well under the stars. And remember, you're connected to them across light years of space and billions of years of time. You're made of them. You're part of them. You're the universe, experiencing itself. What an extraordinary gift that is. So here you are, standing on a planet 7,926 miles across, orbiting a star 93 million miles away, in a galaxy 100,000 light-years across, in a universe 93 billion light-years across. The nearest star is 4.24 light-years away, 25 trillion miles of empty space. You can't cross that distance, not in your lifetime. Probably not in humanity's lifetime if we're being realistic about the physics and the engineering. The universe has set limits, and light years are the measurement of those limits. And yet, you're here. Against all odds, in a universe that's mostly empty space and dead worlds, you exist. You're alive, conscious, aware. You're made of atoms that were forged in the cores of stars billions of years ago. When those stars died, when they exhausted their fuel and could no longer sustain fusion, they exploded. Supernovae, stellar death throes. They scattered their atoms across space, enriching the interstellar medium with heavy elements. Those atoms drifted for eons, for millions of years, maybe billions. They moved through space, part of vast clouds of gas and dust, molecular clouds, star-forming regions. Eventually, they collected into a cloud that collapsed under its own gravity. That cloud became our solar system. The sun and the planets formed from that material. Some of those ancient atoms ended up on Earth, in the rocks, in the oceans, in the atmosphere. And eventually, some of those atoms ended up in you. The iron in your blood, the iron in hemoglobin that carries oxygen through your body, was created in the heart of a dying star. Forged under pressures and temperatures we can barely imagine. Released in a supernova explosion, drifted through space for billions of years, eventually incorporated into Earth, into plants, into animals, into you, the calcium in your bones, the oxygen you breathe, the carbon in your DNA. All of it came from stars. You are, quite literally, made of stardust. This isn't poetic language. This isn't metaphor. It's physics. It's astronomy. It's literal truth. You're made of the remnants of dead stars, recycled and reformed into a person who can look up and understand where they came from, who can know their own cosmic history. You have perhaps 80 years, if you're lucky, maybe 100 with advances in medicine. That's roughly 0.0000006% of the universe's 13.8 billion year history. A blink, a breath, nothing on cosmic scales, an infinitesimal fraction of cosmic time. And yet you're here. You get to experience this moment, this night, this sky full of stars. When you look up, you're seeing across light years. You're looking back in time. Every star is showing you its past. You're connected to distant stars across both space and the fourth dimension, time. That light has traveled for years, decades, centuries to reach your eye. It's crossed unimaginable distances, traversed the void between the stars, and it ends its journey here, with you, creating the experience of seeing a star. Let me tell you what I think light years really teach us. Not just the scale of the universe, not just the distances, not just our smallness, but the preciousness of this moment. You're here, now, on this small world, under these distant stars. You have this moment, this breath, this thought, the problems that weigh on you, the stress, the anxiety, the worry, they're real. I'm not dismissing them. I'm not saying they don't matter. They matter to you, and therefore they matter. But when you feel overwhelmed, when things seem unbearable, when the weight of everything presses down on you, remember, you're experiencing all of this on a planet 7,926 miles across, orbiting a star 93 million miles away, in a galaxy 100,000 light-years across, in a universe 93 billion light-years across. From that perspective, your problems are small, temporary, local, contained to this tiny world for this brief moment. That doesn't make them less real to you. but it might make them more bearable. It might help you breathe. It might give you space to step back, to gain perspective, to see them as part of a larger context. And here's the flip side. The beauty you experience is just as real. The love you feel is just as important. The joy of watching a sunset, light from a star 93 million miles away, scattered through our atmosphere, painting the sky in oranges and reds and purples. The comfort of a friend's embrace, the warmth of human connection across the void, the satisfaction of work well done, of creating something, of making something that didn't exist before, the pleasure of a good meal, simple sensory joy, the peace of a quiet moment, the silence between heartbeats. All of this is happening here, on this small world, and it's precious precisely because of its smallness and brevity. Size isn't everything, duration isn't everything. What matters is what's here, what's now, what you experience in this moment. A light year is 5.88 trillion miles, 9.46 trillion kilometers. It's a distance so vast it defies comprehension. No human mind can truly grasp it. We can calculate with it. We can use it in equations. We can measure the universe with it. But we can't feel it the way we feel a mile or a kilometer. Can't visualize it the way we visualize walking to the store. It's beyond us. Too large, too vast, too far removed from anything in our daily lives. But it's also a reminder. In all that vastness, there's this small world. 7,926 miles across. A dot, a speck, a mote of dust, almost nothing. And on that dot, there's you, living, breathing, thinking, feeling, connected to the stars by light that crosses light years, connected to the past by atoms, forged in stars long dead. Connected to the universe because you're made of the universe, looking at itself, understanding itself. You're small. Yes, your life is brief. Yes, the universe is vast beyond comprehension. Yes, and yet you're here. You get this moment. You get to see this. You get to understand this. That's extraordinary. That's a gift. Let's talk about what light years mean for communication, for the possibility of contact with other intelligences, if they exist. The nearest star is 4.24 light years away. If there's an inhabited planet orbiting Proxima Centauri and there is at least one planet there, Proxima Centauri b, though it's probably not habitable, and if that planet has developed intelligent life, and if that life has developed radio technology, any message we send would take 4.24 years to arrive. Traveling at the speed of light, the fastest possible speed in the universe. If they responded immediately, the moment they received our message, their response would take another 4.24 years to reach us. That's an 8.5-year round trip for a single exchange, for one message and one reply. You could ask a question and not receive an answer until nearly a decade later. You'd send your message as a young adult and receive the reply when you're pushing a middle age. Entire phases of your life could pass while waiting for a response. Relationships would begin and end. Jobs would change. Children would be born and grow into elementary school. The world would transform around you while you waited for an answer from the stars. Any conversation would take place across years, across lifetimes potentially. There's no back and forth dialogue, no real-time exchange, no conversation in any normal meaning of the word. "Hello, we're from Earth" might be sent when you're 25. The response might arrive when you're 33, if they answer immediately. If they think about it first, take time to compose a reply, debate what to say, which any intelligent species probably would. The reply might arrive when you're 40, when you're 50, when you're 60. By the time you send a follow-up and get a second response, you could be retirement age. Your entire career could pass during a handful of exchanges. This assumes Proxima Centauri, the nearest star, the closest possible location for another civilization in our immediate stellar neighborhood. If there's a civilization orbiting a star 50 light-years away, still incredibly close by galactic standards, still in our neighborhood, still one of our near neighbors, each exchange would take 100 years, a full century for one message and reply. You'd send a message as a young adult. Your grandchildren might receive the response, if there is one. You'd never know if your message was received. Never know if there was a reply. You'd send it into the void and die before knowing if anyone was listening. Your great-grandchildren would be the ones to hear back from the stars, to learn if anyone's out there, to receive the response to a message their great-grandfather sent. This fundamentally changes what contact means. It's not a conversation. It's not an exchange in any meaningful sense. It's more like leaving messages for people you'll never meet, hoping they'll someday be found and answered by descendants you'll never know. Messages in bottles thrown into a cosmic ocean. Maybe someday they'll wash ashore somewhere. Maybe someone will find them. Maybe they'll write back. But you'll be long dead before the reply arrives. And this assumes they're using radio signals, which travel at light speed. If they're using some other form of communication, something we haven't discovered or imagined, we might not detect them at all, even if they're broadcasting constantly. Even if they're shouting into space, trying to make contact, we might be deaf to their messages. The SETI project, Search for Extraterrestrial Intelligence, has been listening for decades. Since 1960, 65 years of listening to the stars. They have scanned millions of stars. They've analyzed countless signals, looking for patterns that might indicate artificial origin, looking for the signature of intelligence. They've found nothing conclusive. The famous WOW signal, detected in 1977, remains unexplained, but it never repeated, so we can't study it further. We can't know what it was. It might have been aliens. It might have been a comet. It might have been interference from Earth. We'll probably never know. Maybe we're alone. Maybe intelligent life is so rare that we're the only example in the galaxy or even the universe. Maybe the jump from simple life to complex life is incredibly difficult. Maybe intelligence rarely develops. Maybe technological civilizations tend to destroy themselves shortly after developing advanced technology. Or maybe we're not alone, but the distances are too vast. Maybe there are millions of civilizations out there, but they're all so far apart that contact is effectively impossible. Each one evolving alone, developing alone, dying alone, never knowing about the others. The light years might ensure that every intelligent species in the universe is isolated. Islands of consciousness in an ocean of empty space, forever separated by distances too vast to communicate across meaningfully. Try to comprehend that number. Try to hold it in your mind as a real thing, not just symbols on a page. You can't. No one can. It's beyond human cognition. Our brains didn't evolve to think about numbers like this. But let me try to give you some perspective anyway. If you counted one star per second, one full second to count each star, to acknowledge its existence, it would take you about 6 trillion years to count them all. That's more than 400 times the current age of the universe. The universe would have to exist 400 times longer than it already has for you to finish counting the stars. If every human who has ever lived, about 100 billion people throughout all of history, counted stars their entire lives, and if each person could count one star per second for 80 years without stopping, we still wouldn't come close. We'd count maybe 200 quintillion stars total. We'd still be missing 99.9% of them. The stars are uncountable. Not practically uncountable, literally uncountable in any human timeframe. And we now know from observations by the Kepler Space Telescope and other instruments that most stars have planets. Probably multiple planets. The solar system isn't unusual in this regard. Planets are common. Almost every star has at least one. Many have multiple. Some have dozens. So the number of planets in the observable universe is likely higher than the number of stars. Possibly much higher. Maybe 500 billion trillion planets. Maybe a quadrillion. Maybe more. Imagine that. A quadrillion worlds. Some are gas giants like Jupiter. Huge spheres of hydrogen and helium with no solid surface, with dozens of moons, with massive storms raging in their atmospheres. Some are ice worlds covered in frozen methane or water ice, far from their stars, cold and dark. Some are rocky like Earth, terrestrial planets with surfaces you could stand on, with mountains and valleys and possibly oceans. Some orbit in their star's habitable zone, the region where temperatures are right for liquid water to exist on the surface. Not too hot, not too cold. In principle, these worlds could harbor life. How many of those habitable zone planets exist? We don't know exactly, but estimates suggest billions, perhaps tens of billions just in the Milky Way alone. Multiply that by 2 trillion galaxies, and you get numbers that defy comprehension. Billions upon billions of worlds where life could theoretically exist, where liquid water could flow, where complex chemistry could occur, where, given enough time, simple molecules might organize into complex molecules, which might organize into self-replicating systems, which might evolve into life. And yet, as far as we know, as far as we've observed, as far as we can tell from decades of searching, we found no evidence of life anywhere except Earth. No radio signals from alien civilizations, no artifacts, no signs of large-scale engineering, projects that should be visible at interstellar distances, no unexplained phenomena that clearly indicate intelligence. Either life is extraordinarily rare, perhaps we're alone or nearly alone, or it's common but doesn't develop technology or doesn't last long enough to make contact, or is too far away for us to detect. The distances might ensure that intelligent species are forever isolated from each other, each one arising, developing, perhaps achieving technology, perhaps reaching out into the cosmos, but never making contact, never meeting, never knowing about the others because the light years keep them separated. Islands of consciousness in an ocean of emptiness. This is one of the most profound implications of light years. They don't just measure distance. They measure isolation. They measure the gulf between worlds, the barriers between civilizations. Even if the galaxy, even if the universe teems with life, the distances might mean we'll never know. We'll never meet them. We'll never exchange ideas or culture or technology. We'll never see what another intelligence has created, what they've discovered, how they've answered the questions we're struggling with. We might be surrounded by others, by countless civilizations asking the same questions, looking up at the same stars, wondering if they're alone. And yet, we'll never connect, never make contact, The light years ensure our isolation, or we might truly be alone. The only intelligence in the observable universe, the only consciousness, the only eyes looking out at the cosmos and understanding what they're seeing. Both possibilities are staggering. Both are almost too much to bear. If we're alone, then consciousness is vanishingly rare. Then we're a miracle, an accident, a cosmic lottery win. Then the responsibility of being the universe's only way of knowing itself falls on us. If we fail, if we destroy ourselves, if we render Earth uninhabitable, the universe goes back to being unconscious, to being a vast machine operating according to physical laws, with no one to observe it, no one to understand it, no one to appreciate it. If we're not alone, if the universe is full of life, full of intelligence, full of civilizations, then the distances inshore will probably never know, never meet, never share. Each one isolated in their small corner of space, looking out at the vastness, wondering if anyone else is there. Both possibilities are profound. Both change how you see yourself, your species, your planet. And here's something else to consider. The observable universe is just what we can see from here, from Earth, from our particular location in space. If you traveled to another galaxy, say to a galaxy 10 billion light years away, you'd have a different observable universe. You'd see different regions of space. Some of the galaxies we can see, you wouldn't be able to see because they'd be beyond your cosmic horizon. But you'd see other galaxies that are beyond our horizon that we can't see from here. Every location in the universe has its own observable bubble, its own cosmic horizon, its own view of the cosmos. The actual universe, the total universe, the full extent of everything that exists is likely much larger than the observable universe. How much larger? We don't know. Can't know from observation alone. It might be a few times larger. It might be thousands of times larger. It might be infinite, extending forever in all directions with no edge, no boundary, no end. If it's infinite, then the observable universe, vast as it is nothing. 0% of infinity. No matter how large 93 billion light-years seems, it's infinitely small compared to infinite space. And if the universe is infinite, then everything that's possible happens somewhere. There are infinite stars, infinite planets, infinite copies of Earth, statistically speaking, scattered across infinite space. Infinite versions of you, living slightly different lives, making different choices. This is mind-bending, verging on philosophical rather than scientific. But it follows from the mathematics. If space is truly infinite and matter is distributed roughly evenly on large scales, then given infinite space, every possible arrangement of matter must occur, including arrangements identical to Earth, to you, to this moment. But we can't observe this. We can't see beyond our horizon. We're confined to our observable bubble, our 93 billion light-year sphere. Everything beyond is inference, mathematics, speculation. What we can see, what we can observe, is vast beyond human comprehension. 2 trillion galaxies, hundreds of billions of trillions of stars, perhaps quintillions of planets, and somewhere in all that vastness, on one tiny planet orbiting one ordinary star in one ordinary galaxy, you exist. Against all odds, you're alive, conscious, aware, reading these words, thinking these thoughts, feeling these feelings. You're here. Scientists have even given this future galaxy a name. Milkomeda, or sometimes Milkdromeda, a merger of the two names. But don't worry about the collision. Despite the violent language, it won't be violent at all for individual stars or planets. Stars are so far apart that actual collisions between individual stars are incredibly rare, even when entire galaxies merge. Think about it. The Sun is 93 million miles from Earth. The nearest star, Proxima Centauri, is over 25 trillion miles away. That's an enormous amount of empty space. The distance between stars is so vast that even when two entire galaxies pass through each other, the stars mostly just slip past each other like ghosts. Two clouds of distant lights mingling, some gravitational perturbations, some stars flung out into intergalactic space, some pulled closer to the new galactic center. But actual collisions? Almost impossible. The distances are too vast, the stars too small, and too far apart. By the time Andromeda and the Milky Way merge, our Sun will probably be dead anyway. Long dead. In about 5 billion years, the Sun will exhaust its hydrogen fuel in its core and start fusing helium instead. This will cause it to swell into a red giant. Bloated, cool, luminous. It will expand outward, probably engulfing Mercury and Venus. Maybe reaching Earth's orbit, though the jury's still out on that. Earth might technically survive, but only as a scorched, airless rock. The oceans will have boiled away. The atmosphere will have been stripped off. The surface will be baked to temperatures where lead would melt. No life could possibly survive. Eventually, after a few 100 million years as a red giant, the Sun will shed its outer layers in pulses, creating a beautiful planetary nebula, expanding shells of glowing gas. And at the center, the exposed core will remain as a white dwarf, a dense, Earth-sized ember slowly cooling over trillions of years. So, if humans still exist in 4.5 billion years, and that's a very big if, we'll have long since left Earth. We'll have had to leave. Earth will have become uninhabitable billions of years earlier. We'll probably have left the solar system, maybe even left the galaxy. We'll be observers of the Milky Way Andromeda collision from a safe distance, if we're observers at all. But here's what strikes me about this. We can see Andromeda. On a dark night, far away from city lights, you can see it with your naked eye. Find Cassiopeia, the W-shaped constellation. From there, you can locate Andromeda. It appears as a small, fuzzy oval, not as bright as a star, but definitely visible if you know where to look, and you're away from light pollution. That light has traveled 2.5 million light years to reach you. It's crossed the vast emptiness of intergalactic space, not just interstellar space, but the enormous voids between galaxies. Hundreds of thousands of light years of nothing between the two galaxies, and it arrives at your eye just strong enough to trigger a response in your retinal cells, to send a signal through your optic nerve to your brain, to create the experience of seeing. You're connected to Andromeda across 2.5 million light years of space and time. That light links you to a galaxy that existed before your species did, before your genus did, before most of your family tree existed. When that light began its journey, your ancestors weren't even human yet. The observable universe, the part we can theoretically see, is about 93 billion light years across. About 546 septillion miles, 880 septillion kilometers. Let me be clear about what this number means. It's not just large, it's not just vast. It's beyond the capacity of human minds to comprehend in any meaningful way. We can write it down. We can calculate with it. We can use it in equations, but we cannot visualize it, cannot feel it, cannot hold it in our thoughts as a real, concrete thing. A septillion is a 1 followed by 24 zeros. Try to count to a septillion, one number per second, never stopping, never sleeping. You'd be counting for over 30 trillion years. That's more than 2,000 times the current age of the universe. You could count from the Big Bang until now, over and over, 2,000 times, and still not reach a septillion. And the observable universe is hundreds of septillions of miles across. This isn't the size of the entire universe. It's just how far light has been able to travel since the Big Bang 13.8 billion years ago, accounting for the expansion of space during that time. Think about what that means. The Big Bang happened 13.8 billion years ago. That's when space and time began, when the universe exploded into existence from an infinitely dense, infinitely hot point. Everything that exists now, all matter, all energy, all space itself, was compressed into that initial singularity. Then it expanded. Rapidly at first, the inflationary epoch in the first fraction of a second saw space expand exponentially, faster than light, doubling in size over and over in the tiniest fractions of time. This expansion smoothed out irregularities, created the large-scale structure we see today, and set the initial conditions that would lead to galaxies and stars, and planets, and eventually us. After inflation ended, the universe continued expanding, but more slowly. Space stretched, distances grew. The universe cooled as it expanded, like a gas cooling as it spreads out. For the first 380,000 years, the universe was opaque. It was filled with a hot plasma of electrons and protons, and light couldn't travel far before hitting a charged particle and being scattered. It was like being inside a glowing fog, impossibly hot and bright. Then the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, the universe became transparent. Photons could travel freely. The light from this moment, from the moment the universe became transparent, has been traveling through space ever since. Cooled and stretched by expansion, arriving at our telescopes today as the cosmic microwave background. The oldest light we can see, the afterglow of the Big Bang. Since then, over the past 13.8 billion years, light has been traveling outward from every point in space, and we've been receiving light from the distant regions. But here's the complication. Space itself has been expanding the whole time. Wait, you might be thinking. If the universe is 13.8 billion years old, shouldn't the observable universe only be 13.8 billion light years in radius? Only 27.6 billion light years across? No, because space itself has been stretching, growing, expanding. Imagine you're an ant on the surface of a balloon. You start walking in a straight line at a constant speed. Meanwhile, someone is blowing up the balloon. The balloon's surface is expanding. From your perspective as the ant, you're walking at a steady pace. You're covering ground, but the ground itself is expanding beneath you. So the distance between your starting point and your current position is growing faster than just your walking speed would account for. The balloon's expansion adds to the distance. Now imagine you're a photon, a particle of light traveling through expanding space. You're moving at the speed of light, covering distance as fast as physically possible. But space itself is expanding behind you, stretching the distance you've already covered. So a galaxy that emitted light 13 billion years ago isn't 13 billion light years away now. It's much farther. That galaxy has been carried away by the expansion of space during the time its light was traveling toward us. By the time the light reaches us, that galaxy might now be 46 billion light years away, even though its light only traveled for 13 billion years. The result is that the observable universe is much larger than you'd naively expect, about 93 billion light years in diameter, about 46.5 billion light years in radius. That's as far as we can possibly see, even in principle. Light from anything farther away hasn't had time to reach us yet, not because the light is slow. It's traveling at the maximum possible speed, but because the universe hasn't existed long enough for that light to make the journey. There's a horizon, a cosmic horizon beyond which we cannot see. Not because our telescopes aren't good enough, not because there's something blocking our view, but because the light from those regions simply hasn't arrived yet. And beyond that horizon, we don't know, can't know, might never know. The universe beyond the observable universe is forever beyond our view. We're confined to our observable bubble, our cosmic neighborhood, our local patch of space. Everything beyond is speculation, inference, mathematics, but not observation. Within our observable bubble, this 93 billion light-year sphere, there are approximately 2 trillion galaxies. 2 trillion. Let that number settle for a moment. 2 trillion galaxies. Each one a vast collection of stars, each one containing anywhere from millions to trillions of stars, depending on its size and type. The Milky Way, our home galaxy, has about 200 to 400 billion stars. That's roughly average for a large spiral galaxy. Some galaxies are smaller, dwarf galaxies with only a few million or billion stars. Some are larger, giant elliptical galaxies with several trillion stars. But let's use a rough average. Let's say the typical galaxy has about 100 billion stars. That's probably an underestimate. Many galaxies are larger than this. But let's be conservative. 2 trillion galaxies, each with about 100 billion stars on average. That's 200 billion trillion stars. 200 sextillion stars. A2 followed by 23 zeros. The last time the Sun was at this point in its orbit, dinosaurs were just beginning to emerge. Pangaea was starting to break apart. The Mesozoic era was beginning. The Triassic period. When dinosaurs were small, when mammals were tiny, shrew-like creatures hiding in burrows, when Earth was recovering from the Permian extinction, the Great Dying, which had killed 90% of all species. Since then, the dinosaurs evolved, diversified, ruled Earth for 160 million years, then went extinct when an asteroid struck the Yucatan Peninsula 66 million years ago. Mammals took over, diversified, evolved. Primates appeared, early hominids emerged, humans evolved, civilization developed, and we've circled the galaxy exactly once. One complete orbit, one galactic year. Earth has been around for about 4.5 billion years. That's roughly 20 galactic years, 20 times around the galactic center, 20 complete orbits. In all that time, throughout all those orbits, Earth has remained in this same general region of the galaxy. We've moved through the spiral arms. The galaxy's arms rotate at a different rate than the stars themselves, so we pass through them periodically. But we've always been in the suburbs, always about 26,000 light-years from the center, always in this relatively safe, relatively quiet region. And in all that time, as far as we know, Earth is the only place in the galaxy where life has evolved to the point of understanding what galaxies are. The only place where consciousness has arisen and looked up and wondered about those points of light in the sky and figured out what they are, where they are, how far away they are. We are quite possibly the Milky Way's only eyes, the only way it has to see itself, to know itself, to understand its own existence. The Andromeda Galaxy, the nearest large galaxy to ours, is 2.5 million light-years away. 2.5 million light-years. That's about 14.7 quintillion miles, 23.7 quintillion kilometers. The light you see from Andromeda tonight left that galaxy 2.5 million years ago. 2.5 million years ago, humans didn't exist, not even close. Our species, Homo sapiens, wouldn't appear for another 2.2 million years. We were still deep in our evolutionary past, still becoming what we are. When that light began its journey, early human ancestors, Homo habilis, handy man, were just learning to use stone tools in Africa. They were small, upright apes with brains about half the size of modern humans, about 600 cubic centimeters compared to our 1,300 to 1,400. They probably couldn't speak in any way we'd recognize. They might have had simple vocalizations, calls, warnings, expressions of emotion, but nothing like language. No grammar, no syntax, no ability to discuss abstract concepts, or plan for the future, or tell stories about the past. No art, no culture beyond the most basic tool use, no burial of the dead, no symbolic thought, just survival. Finding food, avoiding predators, reproducing. Since then, while light from Andromeda crossed the intergalactic void, the entire human story has unfolded. Homo erectus evolved, taller, larger-brained, able to control fire and create more sophisticated tools. They spread out of Africa into Europe and Asia, the first human ancestors to leave our home continent. Then Neanderthals and Denisovans emerged, separate branches of the human family tree adapted to different environments. Neanderthals in Ice Age Europe, stocky and strong. Denisovans in Asia, mysterious and still poorly understood. Then us, Homo sapiens, about 300,000 years ago in Africa. Modern humans, anatomically identical to us, same brain size, same body proportions, same capacity for thought and language and culture. We developed language, though we don't know exactly when, probably between 50,000 and 150,000 years ago. The ability to form complex thoughts and share them, to teach, to plan, to imagine, to create stories and myths and explanations for the world. We created art. The oldest known cave paintings are about 40,000 years old, painted handprints and simple figures on cave walls in Indonesia and Spain. People just like us, leaving their marks, saying, I was here, I existed, I saw beauty and wanted to create it. We developed culture, technology, society. We spread across the globe to Europe, Asia, Australia, eventually to the Americas. We survived ice ages and droughts and volcanic winters. We hunted megafauna to extinction and learned to domesticate plants and animals. We invented agriculture about 12,000 years ago, planted seeds deliberately, stayed in one place, built permanent settlements, created surplus food, developed specialization. Not everyone needed to be a farmer, so some could be potters or weavers or priests or warriors. We built cities, created writing, developed mathematics and astronomy and philosophy, built empires, fought wars, made peace, created art and music and literature, developed science and technology. All of that, every human achievement, every thought ever thought by a human brain, happened while light from Andromeda was in transit. And here's something profound. Andromeda and the Milky Way are on a collision course. In about 4.5 billion years, they'll merge. The two galaxies will pass through each other, their stars mingling, their gas clouds colliding and triggering enormous bursts of star formation. Millions of new stars will be born from the compressed gas. The night sky will fill with bright young stars and colorful nebulae. Eventually, after several billion years of gravitational interaction, the two galaxies will settle into a single, large, elliptical galaxy. All the elegant spiral structure will be gone, stirred together into a smooth, elliptical distribution of stars. The Milky Way, our galaxy, is a vast spiral containing somewhere between 100 billion and 400 billion stars. Our Sun is just one of them, one point of light among hundreds of billions. Think about that number for a moment. 100 billion to 400 billion stars. That's not a precise count. We can't count them all individually. Many are too faint, many are hidden behind dust clouds. Some are clustered so densely that we can't distinguish individual stars. So we estimate based on the galaxy's mass, its brightness, its structure. But even the low estimate, 100 billion stars, is staggering. If you started counting right now, 1 star per second, never stopping, never sleeping, counting continuously for your entire life, you'd count perhaps 2.5 billion stars. And you'd still have 97.5 billion to go. You wouldn't even make a dent. You'd barely begin. The galaxy is about 100,000 light-years across, from one edge to the other. From one spiral arm, across the galactic center, across the disk, to the opposite spiral arm, or 100,000 light-years. That's 588 quintillion miles, 946 quintillion kilometers. Let me give you a sense of what this means in terms of travel time, even at impossible speeds. If you could travel at 1% of the speed of light, which would be an absolutely revolutionary achievement, requiring technology and physics far beyond anything we currently possess, crossing the galaxy would take 10 million years. 10 million years. 10 million years ago, our human ancestors didn't exist. The genus Homo, our genus, wouldn't appear for another 7 million years. When this journey began, our ancestors would have been early hominids, distant relatives, barely recognizable as related to us. They were small-brained apes living in Africa, just beginning to walk upright consistently, just beginning to use the simplest stone tools. Over those 10 million years, those apes would evolve into Australopithecus, then into Homo habilis, then Homo erectus, then Homo heidelbergensis, then Neanderthals and Denisovans, and finally us, Homo sapiens. The entire human evolutionary story, from early upright apes to modern humans with language and art and science, would unfold during the crossing. Every ancestor, every evolutionary step, every adaptation, every change that made us what we are today. And you'd still be traveling, still crossing the galaxy, still with tens of thousands of light years to go. If you could travel at the speed of light, which you can't, but if you could, it would take you 100,000 years to cross the galaxy from edge to edge. 100,000 years of traveling at the absolute maximum speed possible in the universe. 100,000 years at 186,000 miles per second. For comparison, modern humans have only existed for about 300,000 years. Agriculture was invented about 12,000 years ago. Civilization is about 6,000 years old. Writing is 5,000 years old. To cross the galaxy at light speed would take longer than all of recorded human history. Much longer. About 20 times longer. You could fit nearly 20 civilizations like ours, from the invention of writing to now, into that time span. And remember, you're traveling at the speed of light. 186,282 miles per second. Nothing can go faster. This is the absolute limit, the cosmic speed limit, the fastest possible speed. At the speeds we actually achieve, the Parker Solar Probe's record-breaking 430,000 miles per hour, crossing the galaxy would take about 154 million years. 154 million years ago, dinosaurs still walked the Earth. The Jurassic period was ending, transitioning into the Cretaceous. The Atlantic Ocean was still forming, still spreading, much narrower than today. Pangaea, the supercontinent, had broken apart relatively recently in geological terms, only about 50 million years earlier. Since then, entire species have evolved and gone extinct. Mountains have risen from ancient seabeds and then eroded back into hills. Continents have drifted thousands of miles. The Atlantic has widened. India has crashed into Asia, pushing up the Himalayas. Australia has separated from Antarctica and drifted north. And you still wouldn't have crossed the galaxy yet. The Milky Way is not just large. It's vast in a way that makes human scales completely meaningless. Think about this. If you could shrink the Milky Way down so that the distance from the Sun to Earth, 93 million miles, was just 1 inch, then the galaxy would still be about 660,000 miles across. That's more than twice the distance from Earth to the Moon. Even when you compress our entire solar system down to an inch, the galaxy remains incomprehensibly vast. Our Sun sits about 26,000 light-years from the galactic center. We're out in the suburbs, so to speak. In a minor spiral arm called the Orion Spur, about halfway between the Perseus and Sagittarius arms. Two of the major arms where stars are born in vast nebulae, where gas clouds collapse under their own gravity, where stellar nurseries create thousands of new suns. We're not in the middle of anything special. We're not at the center. We're not in one of the major spiral arms where most of the action happens. We're out in a relatively quiet region where stars aren't too densely packed, where there's less radiation, less violence, less chaos, fewer supernovae, fewer stellar collisions, fewer disruptions. This position, this unremarkable location, in an unremarkable spiral arm of an unremarkable galaxy, might be one reason life was able to develop here. Think about what unremarkable means in this context. It doesn't mean insignificant. It means safe, stable, quiet enough for complex chemistry to develop without being disrupted, calm enough for billions of years of steady evolution, protected enough for life to experiment, to try different forms, to gradually increase in complexity. Near the galactic center, the environment is hostile. Radiation levels are higher, much higher. The supermassive black hole at the heart of the Milky Way, Sagittarius A star, 4 million times the mass of the Sun, periodically consumes matter and releases enormous amounts of high-energy radiation. X-rays, gamma rays, radiation that would sterilize any nearby planets, strip away atmospheres, break apart complex molecules before life could even begin. Stars near the center also orbit faster, experiencing more gravitational variation as they move through regions of different density. This could destabilize planetary systems over geological timescales. Planets might be ejected from their orbits. Comets might be sent plunging into inner solar systems more frequently. The delicate stability required for life might never be achieved. In the major spiral arms, the environment is chaotic in a different way. Stars are forming constantly in massive nebulae, beautiful to observe from a distance, but violent up close. Young massive stars pour out ultraviolet radiation, ionizing the gas around them, creating glowing regions of plasma. These same massive stars live fast and die young, exploding as supernovae every few million years. Each supernova releases more energy in a few seconds than the Sun will emit in its entire 10 billion-year lifetime. The expanding shockwave can trigger new star formation by compressing nearby gas clouds. But it also bathes the surrounding space in lethal radiation. Gamma rays, X-rays, high-energy particles traveling near light speed. Any planet within a few dozen light-years of a supernova would be in danger. The radiation would hit the atmosphere, stripping away the ozone layer, allowing ultraviolet light to reach the surface at dangerous levels. Life in the oceans might survive, protected by water, but life on land would struggle. The radiation would damage DNA, causing mutations, cancers, extinction. Out here in the Orion Spur, we're sheltered from these dangers. We're between the arms, in a region where star formation is less active. Supernovae are rarer. We can go millions of years between nearby stellar explosions, long enough for life to develop, long enough for evolution to work, long enough for complex organisms to emerge and diversify and eventually develop intelligence. The Sun orbits the galaxy at a steady pace, about 225 million years for one complete orbit. We call this a galactic year or cosmic year. 225 million years. Try to comprehend that timescale. Really try. The last time the Sun was at this exact position in its orbit around the galaxy, Earth was a profoundly different world. It was the late Permian period, just before the Permian-Triassic extinction event, the Great Dying, which would kill about 90% of all marine species and 70% of terrestrial vertebrate species. The largest extinction event in Earth's history. Pangaea, the supercontinent, existed in its full glory. All of Earth's landmass was connected into a single, enormous continent. If you stood on the western shore of what would one day become North America, you could walk east and eventually reach what would become Asia, Europe, Africa, South America. All connected. One giant landmass surrounded by one giant ocean, Panthalassa. The interior of Pangaea was desert, harsh, dry, receiving little rainfall because it was so far from any ocean. Temperatures swung to extremes, blistering hot in summer, frozen in winter. Only the hardiest life survived there. The climate was strange, alien. No ice caps existed at the poles. The planet was warmer overall. Ocean circulation patterns were completely different from today. Monsoon seasons were intense, driven by the massive landmass heating up and cooling down with the seasons. Life existed, but not as we know it. No mammals yet. They wouldn't evolve for another few million years, emerging as tiny, shrew-like creatures after the Great Dying. No birds, no flowering plants, no grass. Instead, reptiles dominated the land. Early archosaurs, ancestors of dinosaurs and crocodiles. Therapsids, mammal-like reptiles, some quite large, some showing the first signs of mammal-like features, differentiated teeth, possibly fur or hair, possibly warm-blooded metabolism. These therapsids were the dominant land animals. Some were herbivores the size of cows. Some were predators with saber teeth. The oceans teemed with life. But again, nothing like today. No whales, no dolphins, no sharks as we know them. Instead, strange marine reptiles, bizarre armored fish, trilobites, though they were declining, on their way to extinction. Ammonites beginning to diversify. Forests existed, but they were forests of ferns and cycads and conifers. No oak trees, no maples, no fruit trees, no flowers at all. Pollination happened through wind, not bees or butterflies, because bees and butterflies didn't exist yet. The sky looked different. The moon was slightly closer, about 12,000 miles closer than today, so it appeared slightly larger. This means tides were slightly stronger. Days were slightly shorter, about 23 hours instead of 24, because Earth's rotation has gradually slowed due to tidal friction with the moon. If you could stand on that ancient Earth and look up at the stars, the constellations would be slightly different. Not dramatically so. 225 million years isn't long enough for stellar positions to change radically, but noticeably different if you looked carefully. Some stars would be in slightly different positions. A few stars visible then might have died since. A few stars not visible then might have become visible as they've moved closer or brightened. That was one galactic year ago. One complete orbit of the Sun around the Milky Way's center. Since then, Pangaea broke apart. The Atlantic Ocean formed slowly over tens of millions of years as the Americas drifted west from Europe and Africa. India, originally part of the southern supercontinent Gondwana, drifted north and crashed into Asia, pushing up the Himalayan mountains. The tallest mountains on Earth, still rising today at about 1 centimeter per year as the tectonic collision continues. Dinosaurs evolved from small archosaurs. They diversified into an incredible variety of forms. Massive sauropods weighing 80 tons, tiny bird-like theropods no bigger than chickens, armored ankylosaurs, horned ceratopsians, duck-billed hadrosaurs. They dominated Earth for 160 million years. Then, 66 million years ago, an asteroid 6 miles across struck the Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs. It created a crater 100 miles across. It triggered earthquakes, tsunamis, wildfires across entire continents. Dust and soot filled the atmosphere, blocking sunlight for months or years. The dinosaurs died. Not immediately, the extinction took thousands of years, but thoroughly. Every non-avian dinosaur species went extinct. Only small bird-like dinosaurs survived, the ancestors of modern birds. Mammals, which had existed as small, mostly nocturnal creatures for over 100 million years, suddenly had an opportunity. With the dinosaurs gone, ecological niches opened up. Mammals diversified, they grew larger, they adapted to different environments, they experimented with different forms and lifestyles. Primates evolved about 55 million years ago. Early primates were small, tree-dwelling creatures with grasping hands and forward-facing eyes, adaptations for life in the trees. They ate fruit, insects, leaves. Over tens of millions of years, primates diversified. Some lineages led to lemurs, others to monkeys, others to apes. About 7 million years ago, the lineage that would lead to humans split from the lineage that would lead to chimpanzees and bonobos. Our last common ancestor with chimps lived then, a creature we've never found fossils of, but whose existence is implied by our DNA. and the DNA of chimps. From that ancestor, the hominin lineage emerged. Australopithecines walked upright and had slightly larger brains. Homo habilis used simple stone tools. Homo erectus learned to control fire and spread across Africa and into Asia. Neanderthals and Denisovans evolved in Europe and Asia, adapting to Ice Age environments. And finally, us, Homo sapiens, appearing in Africa about 300,000 years ago, developing a language, art, culture, spreading across the globe, creating civilizations, developing science and technology. All of that. Every step in the story of life on Earth over the past 225 million years happened during one orbit of the Sun around the galaxy. One cosmic year, and Earth itself has been around for about 4.5 billion years. That's roughly 20 galactic years, 20 complete orbits. Picture the Sun as a runner on a cosmic track, circling the galactic center. Earth has been riding along with the Sun for 20 laps, 20 complete circuits. During those 20 laps, Earth has transformed from a molten ball to a living world, and back and forth through multiple cycles of flourishing and extinction. The first several laps, Earth had no life at all. Just an ocean, an atmosphere of nitrogen and carbon dioxide, volcanic islands, impacts from asteroids and comets. The moon-forming impact happened during this time. A Mars-sized body struck Earth, blasting material into orbit that coalesced into the moon. Then life appeared, probably somewhere between 3.5 and 4 billion years ago. Simple single-celled organisms, bacteria and archaea. They lived in the oceans, getting energy from chemicals or from sunlight through primitive photosynthesis. For billions of years, for many laps around the galaxy, life stayed simple. Single cells, no complexity, no visible organization. If you visited Earth during this time, you'd see an ocean world with no obvious life, no forests, no animals, no fish, just water and rock and sky, with invisible microbes in the water. But those microbes were doing something revolutionary. The photosynthetic ones were producing oxygen as a waste product. At first, this oxygen was absorbed by iron dissolved in the ocean, forming rust that sank to the ocean floor. The banded iron formations we see in ancient rocks today. But eventually, about 2.4 billion years ago, the oceans couldn't absorb any more oxygen. It began to accumulate in the atmosphere. The Great Oxidation Event. From Earth's perspective, this was a catastrophe, a pollution event. Oxygen was toxic to most life at the time. Many organisms died, but some adapted. They learned to use oxygen for metabolism, extracting far more energy from food than anaerobic processes could. This was a breakthrough that made complex life possible. Still, for another billion years, life remained mostly simple. Single cells, though some began to cooperate, forming colonies and eventually multicellular organisms. Then, about 600 million years ago, less than 3 galactic years ago, complex life exploded onto the scene. The Ediacaran period saw the first large complex organisms, strange soft-bodied creatures, unlike anything alive today. Quilted forms, frond-like structures, creatures we struggle to classify because they don't fit neatly into any modern group. Then the Cambrian explosion, about 540 million years ago. Suddenly, life diversified dramatically. Hard shells and skeletons appeared. Predators evolved. arms races between predators and prey drove rapid innovation. Most of the major animal body plans we see today evolved during this relatively brief period. Since then, it's been refinement and diversification. Plants colonizing land about 470 million years ago, creating forests and changing the atmosphere. Insects appearing, amphibians crawling out of the water, reptiles conquering the land, dinosaurs rising and falling, mammals diversifying, humans emerging. And through all of this, the Sun has been steadily orbiting the galactic center, completing its cosmic lapse, carrying Earth along, a small world in tow, circling the great wheel of the galaxy. We've been around the block, so to speak, 20 times. We've seen a lot, and we're still here, still orbiting, still journeying through space together. Earth and the Sun, bound by gravity, traveling together through the galaxy. 26,000 years ago, humans were still hunter-gatherers. We were anatomically modern. Our bodies were the same as ours today. But culturally, technologically, we were living in the Stone Age. The last ice age was ongoing. Glaciers covered much of the northern hemisphere. Neanderthals still existed in Europe, though they were declining on their way to extinction. Woolly mammoths roamed the steppes and tundra. Saber-toothed cats hunted in the Americas. No cities existed, no agriculture, no domesticated animals except possibly wolves beginning the long transformation into dogs. No writing, no metal tools, no civilizations, no governments, no organized religions, just small bands of humans living in a world of ice and megafauna. That's when the light we see from the galactic center began its journey. When these photons left the central regions of the Milky Way and started traveling through space. While this light crossed 26,000 light-years of distance, while these photons traveled through the galaxy toward our solar system, all of human cultural development occurred. All of it. Everything that makes us recognizably modern. The end of the Ice Age, the invention of agriculture, the first permanent settlements, the first cities, the first writing, the Bronze Age, the Iron Age, ancient civilizations rising and falling, Sumer, Egypt, Greece, Rome, China, the Maya, the Inca, the Middle Ages, the Renaissance, the Scientific Revolution, the Industrial Revolution, the modern world. All of it happened while light from our own galactic center was in transit. The Milky Way we see in the night sky, that band of light stretching across the dark when you're far from city lights, is the combined glow of billions of stars. Most are closer than the galactic center, but many are thousands of light years away. When you look at the Milky Way, you're seeing the distant past of our own galaxy. You're seeing stars as they were before recorded history, before civilization, before agriculture, before anything recognizably modern about human existence. You're seeing history, a visual history of our galaxy, written in starlight. The galaxy rotates, but not like a solid disk, not like a wheel. Different parts rotate at different speeds. Near the center, stars orbit faster, completing an orbit in just a few million years. Further out, slower, our sun takes 225 million years. We call this a galactic year, or cosmic year. The time it takes for the sun to complete one orbit around the galactic center. 225 million years. Here's something that will change how you think about looking at the night sky. When you see Proxima Centauri through a telescope, and remember, you need a telescope. It's too faint for naked eyes, too dim to trigger enough photoreceptors to register. You're seeing it as it was 4.24 years ago. Not as it is now, as it was 4 years and 3 months ago. The light you're seeing left that star 4.24 years ago. It's been traveling through empty space ever since, crossing 25 trillion miles of void, traversing the abyss between the stars, until tonight, when it finally reaches your eye. If something dramatic happened to Proxima Centauri right now, in this moment, if it suddenly flared up or dimmed or exploded, we wouldn't know for 4.24 years. The event would happen, the star would change, but the light carrying information about that change would still be in transit, still crossing the vast distance between there and here. For 4.24 years, we'd continue seeing Proxima Centauri as it used to be, not as it is. We'd be looking at a lie, a ghost, an image of something that no longer exists in that state. This is true for every star in the night sky. Every one is showing you its history, not its present. Every point of light is light from the past, arriving now. Sirius, the brightest star in the night sky, is 8.6 light-years away. The light you see from Sirius tonight left that star 8.6 years ago in 2016. Think about where you were in 2016, what you were doing, how old you were, what your life looked like, how different the world was. That's when this light began its journey. When these photons left Sirius and started traveling through space, while you lived your life over the past 8.6 years, this light was crossing the gap between Sirius and Earth, moving at 186,000 miles per second, never stopping, never slowing, always approaching. Betelgeuse, the red supergiant marking Orion's shoulder, is about 700 light-years away. When you look at Betelgeuse, you're seeing it as it was in 1325. 1325, the same year the Aztecs founded their capital city of Tenochtitlan on an island in Lake Texcoco. The same year the University of Oriel was founded at Oxford. The same year that much of Europe was still recovering from the Great Famine of 1315 to 1322. While that light was traveling towards Earth, the Renaissance happened. The Reformation, the Age of Exploration, the Scientific Revolution, the Industrial Revolution, 2 world wars, the Atomic Age, the Space Age, the Digital Age. All of that human history occurred while light from Betelgeuse was in transit. While these photons crossed 700 light-years of space. And here's something remarkable and unsettling. Betelgeuse is a massive star near the end of its life. It's unstable. It could explode as a supernova any time now, astronomically speaking. When I say any time, I mean within the next 100,000 years or so. Maybe tomorrow, maybe next week, maybe in 90,000 years. We don't know, can't know. The physics of stellar death is complex, and we can't predict exactly when this particular star will reach its limit. But here's the thing. It might have already exploded. It might have exploded 200 years ago, or 400, or 650 years ago in 1375, while the Black Death was still killing millions across Europe. And we wouldn't know yet. The explosion would have happened, the star would have torn itself apart in one of the most violent events in the universe, releasing more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. But the light from that explosion would still be traveling toward us, still crossing the 700 light years that separate us from Betelgeuse. Hasn't arrived yet. Won't arrive for years, decades, maybe centuries. So when you look at Betelgeuse tonight, You're seeing a star that might not exist anymore. You're seeing a ghost, an image of something that may have already died 700 years ago, but the news of its death hasn't reached us yet, because the news travels at the speed of light, and light takes time to cross 700 light-years. When it does explode, when Betelgeuse finally reaches the end and goes supernova, it will be spectacular. It will be as bright as the full moon in our sky, visible during the day, bright enough to read by at night. It will dominate the sky for weeks, maybe months, slowly fading as the expanding debris cloud disperses and cools. It will be one of the most dramatic astronomical events visible from Earth in human history. But that event might have already happened, and we're just waiting for the light to arrive, for the news to reach us, for the past to catch up with the present. This is what happens when distance and time become inseparable. The past and present blur together. The idea of now becomes ambiguous, contested, uncertain. What exists right now? What is the current state of the universe? We can't know. We can only see the past. The further out we look, the further back in time we see. The more remote the present becomes, the more it slips away from us, dissolves into uncertainty. Proxima Centauri. It's a small red dwarf star in the Alpha Centauri system, the closest star system to our Sun. Not visible to the naked eye, despite being our nearest neighbor. Too dim, too faint. You need a telescope to see it. The distance? 4.2426 light-years. That's about 25 trillion miles, 40 trillion kilometers. Let me try to give you a sense of this distance, though I know it's futile. I know our minds simply aren't built to comprehend it. We didn't evolve to understand distances like this. We evolved to understand the distance to the watering hole, to the hunting grounds, to the next valley, not the distance to the nearest star. But let me try anyway. If you could somehow travel at 1% of the speed of light, which would be an absolutely staggering achievement, far beyond anything we can do now, requiring technology and engineering that doesn't exist and might be impossible. The journey to Proxima Centauri would take 424 years. 424 years. That's longer than the United States has existed as a nation. Longer than most nations have existed in their current form. It's longer than the gap between now and the 30 Years' War in Europe, which ended in 1648. You'd launch from Earth, and 424 years later, roughly 16 generations later, if we assume about 25 years per generation, your distant descendants would arrive. Everyone who started the journey would be long dead. Their children would be dead. Their grandchildren would be dead. Their great-grandchildren would be dead. Multiple generations, born and raised and growing old and dying during the journey. Great-great-great-great-great-great-great-great-great-great-great-great-great-grandchildren might see the destination, might be the ones who finally arrive. The spacecraft would essentially be a generation ship, a flying world, completely self-contained. The people aboard wouldn't be travelers in any meaningful sense. They'd be inhabitants. This would be their world, the only world they'd ever known. Born in space, living their entire lives in space, working, loving, having children, growing old, dying, all in space. Never setting foot on a planet, never breathing fresh air or feeling rain or seeing a sunset that isn't through a porthole window. Maybe never even thinking of Earth as home, just as stories their great-great-great-grandparents told, as history, as mythology, as a place that might as well be fictional for all they'd ever experience it. And this is traveling to the nearest star, not some distant galaxy, not some unreachable corner of the cosmos, the nearest star. Our next-door neighbor in cosmic terms, the closest other sun in the entire universe. When you look up at the night sky, every single star you can see with your naked eye is part of our galaxy, the Milky Way, our home galaxy. Most are within 1,000 light years. The very brightest, Sirius, Canopus, Arcturus, Vega, are relatively close, cosmically speaking. Sirius, the brightest star in the night sky, is about 8.5 light years away. Arcturus is about 37. Vega is 25. But even these nearby stars are unreachably distant by human standards. Even if we develop technology allowing us to travel at 10% of the speed of light, a staggering achievement that would require physics and engineering we can barely imagine, that would require solving problems we don't even know how to think about yet. The journey to Arcturus would still take 370 years. Longer than the United States has existed, longer than modern science has existed, longer than the Enlightenment, the scientific revolution, the Renaissance. A journey spanning centuries, spanning lifetimes, spanning generations. This is what light years mean. They're not just numbers, they're barriers. Walls between us and the rest of the universe, chasms we can't cross, abysses we can't bridge. The astronomer Carl Sagan once described Earth as a pale blue dot after the Voyager 1 spacecraft turned its camera back toward home from about 4 billion miles away, a distance of just 0.0007 light years. Less than 1,000th of a light year. From that distance, Earth was less than a pixel in size, barely visible. A mote of dust suspended in a sunbeam, as Sagan said. A speck, almost nothing. And that was from within our own solar system, still in the sun's neighborhood, not even close to interstellar space, not even 1% of the way to the nearest star. Imagine viewing Earth from Proxima Centauri, from 4.24 light years away. You couldn't see it at all. Even with the most powerful telescope imaginable, bigger than anything we've built, more sensitive than anything we can conceive, you couldn't pick out Earth. The sun would be visible as a bright star. One star among many, not particularly special. Just another point of light in the sky. But Earth would be lost in its glare. A tiny rock, far too small and too faint to detect. Impossible to distinguish from the overwhelming brightness of the sun. Everything that has ever happened in human history, every empire that rose and fell, every war fought, every work of art created, every scientific discovery made, every love story, every tragedy, every moment of joy, every moment of suffering, all of it happened on a world that's invisible from the nearest star. All of human experience, all of human achievement, all of human history is confined to a world you can't even see from our next-door neighbor. We are unimaginably small, unimaginably isolated. Before we go further, before we travel to the stars, we need to understand what light is, what this speed means, why it matters. Light travels at 186,282 miles per second. In metric, that's 299,792,458 meters per second. Exactly by definition, since 1983, when scientists redefined the meter in terms of the speed of light. We usually round it to 300,000 kilometers per second for simplicity. This is not just fast, it's the speed limit of the universe, the absolute maximum speed, the cosmic speed limit. Nothing can go faster, not spaceships, not particles, not information, nothing. This isn't a technological limitation we might overcome someday with better engines or more advanced physics. It's not like the sound barrier, which we thought was impossible to break until Chuck Yeager did it in 1947. This is different. This is built into the fabric of reality itself, into the structure of space-time, into the fundamental laws that govern existence. Einstein's theory of special relativity, published in 1905, shows that as you approach the speed of light, strange things happen. Things that seem impossible, but have been verified by thousands of experiments over more than a century. Time slows down for you relative to someone standing still. This is called time dilation, and it's not an illusion. It's real. If you flew in a spaceship at 99% of light speed for what felt like 1 year to you, about 7 years would pass on Earth. Your clocks would run slow. Your heartbeat would slow. Your thoughts would slow. Everything about you would be moving through time more slowly. Your mass effectively increases, or, more precisely, your inertia increases. It becomes harder and harder to accelerate you further. The amount of energy required to speed you up approaches infinity as you approach light speed. To actually reach the speed of light, you'd need infinite energy, which means it's impossible for anything with mass. You'd need all the energy in the universe, more than all the energy in the universe. An infinite amount of energy, which doesn't exist, can't exist, is a mathematical impossibility. Only massless particles, like photons, the particles of light, can travel at this speed. And they must always travel at this speed. Photons can't slow down or speed up. They don't accelerate. They don't decelerate. From the moment they're created to the moment they're absorbed, from the moment they pop into existence until the moment they cease to exist, they move at exactly the speed of light. No faster, no slower, always exactly 186,282 miles per second. In 1 second, light travels far enough to circle Earth 7.5 times. In the time it takes you to snap your fingers, about 1/10 of a second, light could travel from New York to Los Angeles and back 37 times. Across the continent and back. 37 round trips, in the time it takes to snap your fingers. In a human lifetime, let's say 80 years, light travels about 564 trillion miles. That's about 908 trillion kilometers. That number is so large, it's essentially meaningless. You can write it down. You can calculate with it. But you can't picture it. You can't visualize 564 trillion miles. No one can. The number is too big. The distance, too vast. It exceeds the limits of human comprehension. But that's how far light travels in the time span of a human life. Now, here's what's profound. We measure cosmic distances in light years. The distance light travels in 1 year. 1 year is 365.25 days. We add a leap day every 4 years to account for that quarter day. That's 8,765 hours, 525,960 minutes. 31,556,926 seconds, if you account for leap years and use the precise astronomical definition of a year. Light traveling for that entire time, 1 full trip of Earth around the Sun, 1 complete orbit, 1 year, covers about 5.88 trillion miles. That's 9.46 trillion kilometers. More precisely, 9,460,730,472,580.8 kilometers. Exactly, by definition. That's 1 light year. It's not a measure of time despite the name, despite having year in it. It's a measure of distance. The distance light, the fastest thing in the universe, the thing that travels at 186,000 miles per second, travels in 1 Earth year. And this distance is so vast that it breaks our ability to visualize it. There's simply no reference point in human experience. Nothing in your daily life is measured in light years. Nothing even close. Nothing even within a billion times close. The Apollo spacecraft that went to the moon traveled at about 7 miles per second on average. At that speed, it would take about 176,000 years to travel 1 light year. 176,000 years. Modern humans, Homo sapiens, have only existed for about 300,000 years. Civilization has only existed for about 12,000 years. Writing was only invented about 5,000 years ago. Agriculture, farming, the foundation of everything we call civilization, has only existed for about 12,000 years. If you started this journey when humans first learned to write, in ancient Sumeria around 3300 BC, when they first pressed wedge-shaped marks into clay tablets to keep track of grain stores and trade goods, you'd only be 3% of the way to traveling 1 light year. Only 3% in 5,000 years of continuous travel at the speed of the Apollo spacecraft. You'd still have another 171,000 years to go, another 97% of the journey, stretching ahead of you into a future so distant it's meaningless. This is the distance we're talking about. This is what a light year means. And the nearest star to our sun is over 4 light years away. 5 hours, 2,800 miles, the entire width of a continent. In 1869, the Transcontinental Railroad was completed at Promontory Summit in Utah. The journey from New York to San Francisco took about 7 days by train, if everything went well. If there were no delays, no washouts, no problems with the tracks. 7 days of watching the continent pass by your window. Before that, if you went overland by wagon, the journey could take 4 to 6 months. Half a year. Crossing terrain that you now fly over in 5 hours. Crossing rivers that could swallow wagons. Crossing mountains that could trap you in early snow. Crossing deserts where water was life and death. The distance hasn't changed. Earth hasn't gotten smaller, but our relationship to distance has transformed completely. The Earth's circumference at the equator is about 24,900 miles, 40,075 kilometers. Early explorers sailed this distance. Ferdinand Magellan's expedition took 3 years, from 1519 to 1522. Not because they sailed slowly, though they did by modern standards, but because they didn't know where they were going. Because they had to search for passages through continents. Because they had got caught in storms and had to shelter. Because sailors got sick and ships needed repairs. Today, if you could somehow book continuous flights around the world, you'd complete the journey in about 45 hours. Less than 2 days. Think about that. The entire Earth, every place you've ever heard of, every city whose name you recognize, every ocean, every mountain range, every desert, every forest, every river. All of it wrapped around a sphere you could circle in less than 2 days. When people first sailed around the world, it proved something profound. Earth is finite. It has limits. You can go all the way around and come back to where you started. The world isn't an infinite plane, stretching forever in all directions. It's not a flat disk with edges you might fall off. It's a sphere, bounded, knowable, traversable. This was revolutionary. For most of human history, people thought of Earth as essentially infinite from a practical standpoint. Yes, there were edges somewhere, oceans you couldn't cross, deserts that would kill you, mountains too high to pass. But the world was so vast that you'd never reach its absolute limits. There was always somewhere further to go, always unexplored territory, always unknown lands. But Magellan's expedition proved otherwise. The world has a size, a definite, measurable size. You can measure it. You can circumnavigate it. You can know it. Earth is large from where we stand. If you're standing in Kansas and looking at the horizon, the world feels enormous, endless. But it's not incomprehensibly large. It's finite, knowable, traversable, measurable. For most of human history, Earth was the universe. The ground beneath, the sky above, that was everything. That was all that existed. The stars were just lights on a dome overhead, beautiful, mysterious, useful for navigation, but just lights. Decorations on the ceiling of the world. No one knew what they were. No one knew how far away they were. They might be a few miles up, attached to a crystalline sphere that rotated around Earth. They might be holes in a dark curtain, letting light from heaven shine through. They might be campfires of the gods. They might be any number of things. Ancient Greek philosophers estimated the moon might be about 200,000 stadia away, roughly 24,000 miles in modern units. They weren't far off, actually. Their estimate was in the right ballpark. But they had no way to check their calculations, no way to actually measure it. It was educated guessing based on geometry and assumptions. But now we know. Earth is just one planet, one world among countless worlds. And when we measure the distances to other worlds, to stars, to galaxies, that's when something changes. That's when the distances start to slip away from you. When the numbers stop meaning what you think they mean. When your intuition for distance breaks down completely. But before we get there, I need to show you exactly where and how it happens. I need to show you the precise moment when comprehension breaks down. When the familiar becomes alien. When distance becomes something else entirely. Our star, the source of all light, all warmth, all life on Earth. The gravitational anchor holding our planet in its orbit. The reason we exist. The reason anything exists on this world. The Sun sits 93 million miles away from Earth. That's 150 million kilometers. We call this distance one astronomical unit, abbreviated AU. It's one of the fundamental measurements in astronomy, the baseline against which we measure everything else in the solar system. 93 million miles. Can you picture 93 million miles? Can you hold that distance in your mind? I'll give you some comparisons to try to make it concrete, but notice, really notice, how your mind responds to them. Notice how the comparisons might help a little, but don't really convey the distance. Don't really make you feel it. At highway speeds, 60 miles per hour, driving continuously without stopping, without sleep, without running out of road somehow, you'd reach the Sun in about 176 years. 176 years. Let that sink in. Not 176 hours. Not 176 days. 176 hours. The United States declared independence in 1776. If someone started driving from Earth to the Sun that year, the year of the Declaration of Independence, when the nation was born, when the Founding Fathers signed that document in Philadelphia and drove continuously at 60 miles per hour without ever stopping. They'd be arriving at the sun right now, in 2025, 249 years later. They'd have driven through the entire history of the United States. The Revolutionary War, the battles, the suffering at Valley Forge, the victory at Yorktown, the drafting of the Constitution, the bitter compromises over slavery that would later tear the nation apart. The Louisiana Purchase, which doubled the size of the country overnight. Westward expansion, the Trail of Tears, the Oregon Trail, the Gold Rush, the displacement and destruction of indigenous peoples. The War of 1812, the Mexican-American War, the Civil War, 650,000 dead, cities burned, the country splitting in two, and then painfully knitting back together. Reconstruction, the Gilded Age, the rise of industry, robber barons building empires while workers labored in dangerous conditions. The Progressive Era, World War I, the Roaring Twenties, the Great Depression, a quarter of the population unemployed, breadlines, despair. World War II, the Holocaust, the atomic bomb, the post-war boom, the civil rights movement, marches, violence, slow, painful progress toward equality, the Cold War, Vietnam, Watergate, the fall of the Berlin Wall, the First Gulf War, September 11th, the War on Terror, the Great Recession, the rise of smartphones and social media, the pandemic. All of that history, every president, every war, every invention, every social movement, every triumph and tragedy would pass while they drove. While they covered 93 million miles, generations would be born and die. Technologies would be invented, flourish, and become obsolete. The world would transform completely, multiple times over. Horses and carriages would give way to cars. Cars would become ubiquitous. Letters would give way to telegrams, telegrams to telephones, telephones to emails, emails to texts and instant messages. Candles and gas lights would give way to electric lights. Mechanical calculators would give way to computers the size of rooms, which would give way to desktop computers, which would give way to laptops, which would give way to smartphones more powerful than the computers that sent men to the moon. And through it all, the driver would still be driving, through vacuum, through absolute emptiness. 93 million miles of nothing. No landmarks, no rest stops, no scenery, just distance. But we have faster ways to travel. The Parker Solar Probe, launched in August 2018, reaches speeds of about 430,000 miles per hour at its closest approach to the Sun. That's roughly 692,000 kilometers per hour. That's a genuinely absurd speed. It's the fastest human-made object ever created, the fastest thing humanity has ever built and sent into space. At that speed, you could circle Earth in about 3.5 minutes. The entire planet, all 24,900 miles of circumference, in 3.5 minutes. New York to Los Angeles, 2,800 miles, would take about 23 seconds. Let me say that again. 23 seconds to cross the United States. Less than half a minute. And yet, even moving at this absolutely incomprehensible velocity, a speed that would seem like magic to anyone living before the space age, a speed that breaks every human intuition about motion and distance. The Parker Solar Probe still takes months to complete its orbits around the Sun. because 93 million miles is vast. Even at speeds we can barely comprehend, it's vast. Even at speeds that turn continents into brief moments, it's vast. The probe doesn't travel in a straight line to the sun. That would require enormous amounts of fuel to fight against the sun's gravity, to slow down enough not to just fall straight in. Instead, it orbits in a carefully calculated ellipse, using Venus's gravity in a series of flybys to gradually adjust its trajectory closer and closer to our star. Each orbit takes months. The closest approaches, the perihelion passes, when it's closest to the sun, last only hours, precious hours when it's inside the sun's corona, measuring things no spacecraft has ever measured before, experiencing temperatures no human-made object has ever withstood. But here's what makes this distance feel real in a way that numbers never can. Light from the sun takes 8 minutes and 20 seconds to reach Earth. Right now, as you listen to these words, if you stepped outside and looked at the sun, please don't look directly at it, but if you were observing it safely through proper filters, through eclipse glasses or a solar telescope, you'd be seeing the sun as it was 8 minutes and 20 seconds ago. Not as it is, as it was. Think about what that means. Really think about it. If the sun suddenly exploded, if something catastrophic happened to our star right now, in this very moment, we wouldn't know for 8 minutes and 20 seconds. The explosion would happen 93 million miles away, and the light carrying information about that event would still be traveling toward us, still crossing the vast emptiness of space at 186,000 miles per second. For 8 minutes and 20 seconds, we'd continue our lives normally. The sun would still appear to shine in the sky. The sky would still be blue, lit by light that left the sun before it died, but would birds still sing. Traffic would still flow. People would still go about their business. Everything would seem fine, normal, safe. And then, 8 minutes and 20 seconds later, the light from the explosion would arrive. The sky would change. Everything would change. And we'd realize in that moment what had happened 8 minutes and 20 seconds in the past. By the time we knew, it would already be too late. The disaster would already have occurred. Nothing we could do, nothing we could have done. The past reaching forward to claim the present. This is what distance means when you approach cosmic scales. It's not just space, it's time. The two become inseparable, merged, unified. Every time you look at something in space, you're looking backward in time. The farther away it is, the further back you're seeing. Distance and time are the same thing when light travels at a finite speed. The sun is 8 minutes and 20 seconds in the past, always. When you see sunrise, you're seeing the sun as it was 8 minutes and 20 seconds ago. When you see sunset, same thing. When you feel the warmth of sunlight on your face at noon, that warmth left the sun 8 minutes and 20 seconds ago. You're never seeing the sun as it is right now. You're always seeing its history, its past. This creates something strange. The present moment, the now, becomes ambiguous in space. What does right now even mean when we're talking about the sun? Do we mean the sun as it exists at this instant? Or the sun as we 8 minutes and 20 seconds delayed. There is no universal now in the cosmos. The present moment is local. It only makes sense here, where you are. The further out you look, the further back in time you see. The more the present slips away from you, dissolves into the past. The moon orbits us at an average distance of 238,000 200,855 miles. That's 384,400 kilometers. Let that number sit for a moment. 238,855 miles. Try to visualize that. Really try. You can't, can you? Your mind might reach for comparisons. It's like placing 30 Earths in a line between here and there. That's how much empty space exists in that gap. 30 entire planets, each one 7,900 miles across, lined up end to end. 30 globes the size of Earth, touching edge to edge. And even that description, 30 Earths, doesn't really help. Because you can't visualize 30 Earths. You can picture one Earth, maybe. A blue marble hanging in space, maybe two Earths, one next to the other. But 30? Your mind can't hold that image, can't construct it, can't see it. The number is too big. The visualization fails. And we've only just started. When you look at the moon in the night sky, it looks close, intimate, almost. You can see its features with your naked eye. Craters, dark patches, the Luna Maria, the seas, though they're not actually seas, but vast plains of ancient lava that erupted billions of years ago when the moon was young and hot, then solidified and darkened, darker than the surrounding highlands. With binoculars, you can see mountains, valleys, crater rims sharp against the black sky. You can see where asteroids impacted billions of years ago, carving out circular basins that filled with lava. You can see the rays of material that splashed out from impacts, bright streaks radiating from fresh craters. It looks like you could reach up and touch it, like it's just beyond the clouds, just past the edge of our atmosphere, like it's near, but it's not. It's 238,855 miles away. That distance is so vast that if you drove there at highway speed 60 miles per hour steady, never stopping, it would take you 165 days, 5.5 months of continuous driving, through vacuum, through emptiness. The Apollo astronauts needed 3 days to cover this distance, traveling at 25,000 miles per hour, about 40,000 kilometers per hour. That's 400 times faster than highway speed. 400 times faster than you've probably ever driven. Think about what that speed means. If you could drive at 25,000 miles per hour on Earth, you could go from New York to Los Angeles, that 2,800-mile journey we talked about earlier, in about 6.5 minutes. 6.5 minutes to cross an entire continent, to cross the width of North America from ocean to ocean. Or you could circle the entire Earth at the equator in about 60 minutes. 1 hour to go all the way around the planet, to pass over every longitude, every time zone, seeing them all in the span of a single hour. Faster than the International Space Station, which orbits Earth every 90 minutes at about 17,000 miles per hour. And yet, at 25,000 miles per hour, at this absolutely staggering velocity that makes highway speed look like standing still, it still takes 3 days to reach the moon. 3 full days, 72 hours. The astronauts would launch from Earth, the massive Saturn V rocket accelerating them to this incredible speed. And then for 3 days, they'd be in transit, sleeping in shifts, eating freeze-dried food, checking systems constantly, floating in microgravity in a space the size of a small car, looking out the window and watching Earth slowly shrink behind them, watching it change from the overwhelming presence that fills your entire field of vision to a blue marble, then to a small blue dot, then to just another bright star in the blackness, while ahead of them, the moon slowly, gradually grew larger. Hour by hour, barely, perceptibly, it would expand in the window. From a distant disk to something showing detail, to something looming, to something you could see you were approaching. Imagine what that feels like. You're moving at 25,000 miles per hour, faster than anything most people will ever experience, faster than any car or train or conventional aircraft could ever go, and yet your destination barely seems to get closer. Hour after hour, the moon grows in the window, but only gradually, slowly, so slowly. It takes patience, faith that the mathematics are correct and you're actually making progress, faith that the numbers on the navigation computer are accurate, that you really are closing the distance, even though it doesn't feel like it. Even though it looks like the moon is staying the same size, the same distance away, hour after hour. Here's something that makes the distance real, something intimate and human about that vast, empty gulf. When the astronauts on the moon spoke to Mission Control in Houston, there was a communication delay. Every word had to travel 238,855 miles as a radio signal. Radio waves travel at the speed of light, 186,282 miles per second, or about 300,000 kilometers per second. Even at this incredible speed, the signal took 1.3 seconds to make the journey. When Mission Control replied, another 1.3 seconds for the return journey. Nearly 3 seconds total for a single exchange, for one back and forth of communication. If you listen to the old recordings from the Apollo missions, and you can find them online, NASA has archived everything, every word spoken between the astronauts and Earth. You can hear this delay. It sounds almost awkward, like people being overly polite, waiting an extra beat before responding. An astronaut will say something. "Houston, we've got good contact light." There's silence. Dead air. Then Mission Control responds. "Roger, we copy Columbia." More silence. Then the astronaut acknowledges. "Roger." Another pause. It's not politeness. It's not hesitation. It's not people gathering their thoughts or choosing their words carefully. It's physics. It's distance. It's the speed of light multiplied by 238,855 miles divided by 186,282 miles per second. Even light, the fastest thing in the universe, the cosmic speed limit, the thing that travels at 186,282 miles per second, takes time to cross 250,000 miles of empty space. Even at speeds that make our fastest rockets look like they're standing still, distance takes time to cross. Space has extent, depth, volume. And this is important to notice. We've only gone to the moon. We're still in Earth's immediate neighborhood. We haven't even left the Earth-Moon system yet. We're still within what astronomers call cislunar space, the region between Earth and its natural satellite. We're basically still at home, still in our front yard, and already the distance is becoming strange. Already the numbers are too large to feel. Already we're feeling the edges of our comprehension start to fray. Already distance is becoming abstract rather than concrete, a number rather than an experience. Now, let's go to the sun.